All right, guys. Good afternoon. Today I'm going to go over modern physics, just the required topics for this course, which is the introduction to quantum physics. Possibly at the end, I can go and talk a little bit about um, atomic physics, just as an extra, depending on how much time we have left. So with modern physics, you can find the slides that I'm gonna use in modules. They will be located in here. All right. Don't worry about this. I'm actually gonna be using some of these problems today. All right. Also from here. So even though there are no assignments for quantum physics, for relativity, and for atomic physics, you can use this to practice problems and also the sample final, as I show you before. You can find it in here. All right. Now, granted, these topics starting today are not very, like, we don't really test as many, or we don't really ask as many questions on these topics as from the previous topics, right? In a 30 question final exam, this one has 60 questions, but the final that you guys will have 30 questions. There might be just one or two. All right. The big part of the exam comes from electrostatics to diffraction and interference, which are the topics of your 16 assignments. Okay. So by doing those and reviewing the previous evaluations, you should be more than prepared for the final exam. All right. So modern physics is more like extra information. All right. For you guys to know, to be introduced to these new ideas of physics. Okay. So what we're going to be covering are new ideas relative to Newtonian mechanics and classical mechanics, right? Because I'm going to be explaining and teaching you a few ideas that were introduced at the beginning of the last century, like the whole idea of the photon, the photoelectric effect, the Compton effect, and then the de Broglie and the Heisenberg uncertainty principle. Okay. So those are the main topics of this unit, of this chapter. All right. So let's show you what I have here on the whiteboard. Here I have a summary of the slides with some extra information. The first idea that you should learn in this chapter is the idea of the black body radiation. Now, black body radiations are particularly important when we study stars. And that's why I want to go into atomic physics a little bit today, because there is some applications of what we did before, like the de Broglie experiment, the idea of diffraction, and the emission and absorption lines, which are related to the visible spectrum. So there is a relationship with what we did before. But we need to understand what is a black body radiation, a black body curve. So a black body absorbs all incident light, and it's also an ideal radiator. So when we are characterizing or studying a star like the sun, we end up using a graph like this. This is known as the Planck curve, because it was discovered by Planck theoretically to explain observations of emission of radiation of black bodies. So what this shows you is that when you graph the intensity versus frequency, which, by the way, in quantum mechanics, the symbol for frequency changes to this. It's like a V, right? It's a Greek letter, And we use that because F is used a lot for many other variables. Recently, F was the focal length, right? So in quantum mechanics, we start introducing a lot of the Greek symbols like sigma, right? Like deltas, right? And that's the one that we use for frequency. So frequency in hertz, or even wavelength, there you go, lambda. You can have down the x-axis. Just remember that for an electromagnetic radiation, lambda times frequency is equal to the speed of light. So you could change this to lambda by doing the conversion c over lambda, which I'm gonna show you over there later. So you can have the x-axis as frequency or lambda. If you have this graph, the equation that Planck discovered for this theoretical curve is given here. Now, you don't have to memorize, and we are not technically gonna use this equation. However, for black bodies that have different frequencies of radiation and a given temperature for it, you can do this graph. So this graph depends on two variables, right? The frequency and the temperature, just as you see here, right? You have the intensity that is related to the energy radiated, as we will see later, and the frequency or wavelength. You can also write the equation for Planck's curve as a function of wavelength and temperature. All right? Now, why is this equation important? It's important because this leads you to what we know as an ultraviolet catastrophe. So classically, you don't have this equation in the slides, but this equation is the one that we use to find the power radiated by a body in space. In fact, macroscopically, we still use this equation to find the luminosity of a star. So if I want to find the luminosity of a star, which is the rate of energy radiated, in other words, the power radiated by the star, we see that it depends on the size of the star, on the Stefan Boltzmann constant, and the fourth power of temperature in kelvins. So there are a few things here, right? Temperature now in quantum mechanics and also in relativity in astronomy is measured in kelvins. We don't use Celsius, we don't use Fahrenheit. So these equations are built when radius is in meters, temperature is in kelvins, and then the Stefan Boltzmann constant is also in units of meters, joules, and kelvins, right? So classically, if I were to plot the intensity as a function of temperature, and recall that classically power divided by area was the intensity, right? We did this before, so that's okay, classically. So intensity is proportional to power. So we can plot intensity as a function of temperature, and because of this relationship, it's going to be recorded. Okay? Because of this relationship, as the temperature increases, the intensity will increase. And theoretically, it should keep increasing. But the ultraviolet catastrophe shows you that at certain peak, the intensity will flatten and then it will decay. So it reaches what we know as a peak. So this will be your peak frequency related to a peak intensity. So if there is a peak frequency, there should be, according to this, a peak temperature, right? If we take the limit when the temperature becomes very large, then this will be e to the 0, 1 minus 1. So you get a horizontal asymptote, sort of, right? So when h times frequency is equal to the Boltzmann constant, you should know this because this equation here is energy, as we will see here, and this is also energy. That was what you probably remember this from the kinetic theory of gases. The kinetic energy of gases is 3/2 of kT. Well, this was the Boltzmann constant, right? So that's where you have this. So units of energy, units of energy. So there is a point where if you have a peak frequency, you will have a peak temperature. That's what we also observe here, right? So we analyze black body curves for stars, for example, by looking at the peak. That peak will give us the frequency where the peak radiation is being emitted. And if we know that, we can find the peak temperature. That is basically Wien's law, all right, that you see over there. Wien's law relates the wavelength and the peak temperatures or the peak frequency. Now let's look what the relationship is. Lambda times temperature at the peak of the black body curve is equal to that constant, 0.00290 meter kelvins. So these are the units. So this is very useful because when we analyze stars, we can look at their black body curve, and normally we can find the peak frequency or temperature, or wavelength. If I find a peak wavelength, I can use it to find the peak temperature of the energy radiated by a particular object. Now, we know that the speed of light is equal to lambda times frequency, right? Now, the speed of light is approximately 3 times 10 to the 8 meters per second. So I can change, like I mentioned here, this equation by doing lambda equals to C over frequency, and then I can find that the frequency at the peak is equal to 5.88 times 10 to the 10 times the temperature at the peak, where the frequency is in hertz. All right? So there are two ways to express Wien's law. So that's the first equation or relationship that we find in quantum mechanics or quantum physics. All right? So the understanding of the black body radiation leads to the idea of how different the relationship between intensity, frequency, and temperature is in quantum physics and classically, and also how this leads to the quantization of light. The quantization of light is the idea that the energy of light comes in small bundles or small packets or bundles of light that we call photons. So here is where the whole idea of photons comes from. A photon is the fundamental particle of the electromagnetic radiation. So you now know already from what we studied before what an electromagnetic wave is. Electrons being accelerated in an electromagnetic field will radiate electromagnetic waves. Now, the electromagnetic wave carries energy and momentum. this energy and momentum is due to these particles, these fundamental particles, which are photons. But we know also by the Young WSD experiment that light has a wave-like behavior. So here is where you're gonna learn the dual behavior of light. We have studied light as a wave, and it was more clear when we did the studies of interference and diffraction, how you can make light go through two slits, and then you see the interference pattern. Or if you have just one slit, or if you have a diffraction grating, and then light goes through it, and you see the bright and dark fringes, right? So that's the study of light as a wave. All this and then this leads to the study of light as particles, as a stream of photons. And what you're seeing here is the energy of a photon. The energy of a photon is equal to h times 1. Frequency will be this, right? Now, h was introduced here already, and h is known as the Planck constant. This is the Planck constant, which is equal to 6.626 times 10 to a negative 34 joules second. So this is the thing though. Macroscopically, is almost irrelevant to talk about the energy of a photon because it's going to be very tiny. So macroscopically, we can stick to the classical definitions of energy and intensity to understand, well, to understand everyday experiences, even light, even the intensity of an electromagnetic wave, right? We can use the classical definitions. However, there are experiments that led us to believe or to understand that we need to understand the quantization of light to make sense of the results of those experiments. This is one of those. It's one of the observations, the ultraviolet catastrophe, and the relationship between the wavelength and the temperature of a black body. That's one of those. The other one is the photoelectric effect. So the photoelectric effect, in general terms, is the idea of electromagnetic radiation at different wavelengths is striking pieces of metal, and depending on the frequency of light, as you change it, electrons can be ejected from the pieces of metal. Of course, this depends on the material of the metal. It can be silver, it can be sodium, it can be potassium, it can be gold. But at the end of the day, you can have photoelectrons, that's actually the correct name, being ejected only when you have only when you achieve a limit, or what we know as a threshold or a cut-off frequency of the incident light. And that's the experiment that allowed Albert Einstein to win his Nobel Prize. And that's why scientists around the world, especially in the 1920s, they saw Einstein as the person who opened the door to quantum physics. Of course, in history, he decided to deviate from that and take his own path, because as quantum physics and quantum mechanics, the studies of this branch of physics evolved, we went into the idea of probability, right? One of the differences between quantum physics or quantum mechanics and classical physics and obviously relativity is that in classical physics and relativity, we have a set of laws and results, a set of equations that give us results that we can check with observations and experiments. With quantum mechanics, we have experiments, we have observations, but the study of the behavior of an electron or particles, right? They rely in the probability equation and the equation of the wave. That's the whole idea of the Schrodinger equation and the Heisenberg uncertainty principle and so on. So that is one of the differences between quantum mechanics and classical physics / relativistic physics, which we're going to do tomorrow. So that is the problem. And that's why Einstein decided to, even though he discovered and he opened the door to quantum physics, he decided to take his own path. All right? So that's basically the introduction summary of what we have today. So in the slides, they show you a few graphs. So what do you see in this graph? What you see in this graph of the black body curve, you see that as the peak temperature increases, the black body will become steeper. And look how the infrared, the visible, and the ultraviolet parts of the spectrum are placed in there. This is important because this allows you to understand the relationship between the electromagnetic spectrum and the temperature at which we can graph this black body curve. Now, you have different temperatures, and these are chosen because of what we know from astronomy. The peak temperature for the sun, for example, right? The surface temperature of the sun is approximately 6,000 kelvins. So we can find the peak frequency and the peak wavelength of the radiation emitted by the sun by using Wien's law. All right? So here it is, Wien's law. That's the equation that gives you the frequency at the peak, as you see here. Right? And one of the conclusions of this was that the distribution of energy in a black body radiation is independent of the material. It depends only on the temperature. All right? Now, the description of this Wien's law is that as you increase the temperature, the frequency will also increase linearly, right? Because the constant between the peak frequency and the peak temperature is 5.88 times 10 to the 10. There. All right. And look at the units of the constant, right? Seconds to the -1 or hertz, and kelvins to the -1. So all these values, all these constants are given in those units. Now, this is what I was talking about, the classical prediction and the experimental observations and the Planck's prediction. The Planck's prediction fits very nicely with the observations that we have from objects radiating as a black body radiators. The classical prediction, however, has a huge discrepancy, which allow us to change our views, our classical predictions with respect to the quantum predictions given by this. And here is the discovery from Planck, the fact that the energy is quantized and depends on frequency or wavelength. Because if you think about it, right? This equation here, using this, you can change it and find the two equations for the energy of a photon. So if you want to find the energy of a photon, all right? The equation that we use is equal to h times frequency, but frequency is c over lambda. So that's another equation that we are going to use today, depending on the information you're given. They can tell you that you have light with a wavelength of 450 nanometers. So we can find the energy with this. H is a Planck constant, and we know C, well, C is the speed of light. So that's how you find the energy of a photon. If you have more photons, then that's when you put the N. And you're gonna realize later, or you're gonna see later, that N is the first quantum number. There are 4 quantum numbers which are solutions of the Schrodinger equation, right? N is the principal, then you have the L, the ML, and S, right? Each one contributes to different properties of the electron, right? The principal, which is related to the energy. You have the L, which is the symbol that we use for the angular momentum. You have ML, which is the magnetic energy or magnetic spin, and S is the spin. All right? So those are important results that we obtain from the quantization of light. Now, it's expected that the energy of a photon, you're gonna see that are going to be very small. So we need to introduce ways to find or to write these small values of energy. You should recall from chapter 16 the idea of an electron volt, which is EV. An electron volt is the energy, so this is the amount of energy required by one electron to change its potential by 1 volt. For a change on potential equals to 1 volt. You remember that the energy, which is the change on the work done by the electric force, which is the change on energy, is equal to QV. Well, 1 electron times 1 volt, that's your 1 electron. Now, why is this important? Because I know the charge of the electron. So in joules, this will be 1.60 times 10 to a negative 19 joules. So in quantum physics, we are going to be using a lot energies in electron volts or mega electron volts. And that's how we do the conversion. 1 EV is equivalent to 1.60 times 10 to a negative 19 joules. Okay? That's what we have. Okay, so in the slides, they show you the energy of a photon or frequency. Okay, if they use F in here, it's fine. Just remember that depending on the textbooks that you use, either F is a label for frequency or it might be that V that I'm using on the whiteboard, all right? So let's talk a little bit about the photoelectric effect before we do examples of this. So, as I mentioned, in the photoelectric effect, you're gonna have beams of light. And as you know already, these beams of light are a stream of photons. And here is where we have the differences between the classical definition and the quantum understanding. In the classical definition, you increase the energy by increasing power, by increasing the intensity. In the quantum definitions, the intensity doesn't really depend on the energy, because the energy of a photon depends on the wavelength or the frequency. So the energy is irrelevant or is sort of independent of the intensity. The intensity just tells you the amount of photons in a given beam of light. The more photons, the more intensity. But that doesn't mean that the energy will change. You are seeing it right now illustrated in front of you. So each photon is characterized by a wavelength. As you know, the energy of a photon is equal to h frequency or hc over lambda. So you can have photons with a given wavelength. If you increase the wavelength, you are reducing the energy, but the intensity can remain the same, because the intensity depends on how many photons you have in a given beam of light. So this is the key aspect for the photoelectric effect. What Einstein did in this experiment is he changed the frequency, aka the wavelength of light, that was aiming towards a collector, as you see in there. You have an emitter and you have the collector, which are basically two parallel plates. When you do that, as you know, there's going to be an electric field, and the electric field is going to push the electrons. Now, if you have electrons moving, you are going to have current. So the current is measured by the ammeter. So basically, you have a circuit. Now, depending on the current, you know the amount of photoelectrons being emitted by the incoming light. What Einstein discovered is that the energy of the photoelectrons was equal to the difference of the emitted light, so the energy by the photons being emitted, and the work function of the metal. So the work function is a property of different metals. Okay, it's like friction, right? The more friction, the less energy you will have for the electrons to flow. Now, how do you change the energy though? As I said here, you don't change the energy by changing the intensity of the beam. You change the energy by reducing the wavelength or increasing the frequency. So that's the difference between the classical predictions and the observations. Any beam of light of any color can eject electrons. So this means that you can have color red or blue. If you increase the intensity, classically, you will increase the energy. That means that you can eject electrons. False. Because blue light has more energy than red light. Blue light has a shorter wavelength. So blue light will emit photoelectrons. Red light may not. The maximum kinetic energy of the photoelectrons will increase as, well, we know this from part 1, right? The kinetic energy increases as you increase the frequency, all right? So there must be a minimum frequency. We call that a cutoff frequency for photoelectrons to be ejected. Now, at that given frequency, once you start ejecting photoelectrons, as you increase the number of photons, the number of electrons will have the same energy. So that was the observation, that you can increase the number of photons, but because each photon has the same energy, the same E, the kinetic energy max won't change. So that's crucial to understand that light is quantified, that Planck was correct, and well, basically, because of this simple experiment, looks or sounds simple, but I mean, it's really not. Einstein won his Nobel Prize in 1916, 1917. You probably remember this famous picture of the fathers of quantum physics, Bohr, Heisenberg, Marie Curie, de Broglie, Planck, and Einstein in the middle. You can find it on the internet. It's all over the internet. Right?
Wasn't that photo taken at the convention in Switzerland?
So what is this kind
Switzerland,
of
I think.
frequency, right? Is a frequency, the minimum frequency is required, depending on the metal, to eject photoelectrons. And that's easy to prove if we write the photoelectric effect. So if we write the photoelectric effect, the way I like to write this is like this, okay? I want you to say the photoelectric effect states that the energy emitted by a beam of light is equal to the maximum kinetic energy of the electrons plus the work function. All right? Now, if you want to find the cut-off frequency for this, so if you want to find this, that happens when the kinetic energy of the photoelectrons is 0 joules. If that's the case, then you have that the energy using the equation there is HF equals to the work function. So the work function, or the cutoff frequency, is the work function divided by H. So what you can plot in a graph, right? What you could plot in a graph, and that's what Einstein did for different metals. He bombarded different metals, right, with a given amount of energy. So you can plot energy as a function of frequency. So if you plot the energy as a function of frequency, this is linear, right? HF equals to W. So the slopes will always be the same. This slope will be the same as this. But there are different cutoff frequencies. This can be gold, this can be silver. It depends on the metal. The slope will be equals to H, which is a constant, it's a Planck constant. All right. So this is the first experiment that shows that light behaves as a particle as well. Because you have here the conservation of energy between light and electrons. So they are interacting as particles. As you know from chemistry, an electron that is orbiting the nucleus of the atom absorbs a photon and can get into an excited stage. And it can be a transition, right? From the ground state to the first, second, etc., etc. We know that as energy levels. Now, Bohr is the one who did the study of that with the hydrogen atom. And even though we know that it only works for the hydrogen atom, the idea of energy levels is still considered correct. That there are some energy levels allowed states for the electrons to be located. Now, We know that the electron doesn't really orbit the nucleus of the atom, as I spoke about in the first day of class. We have this electron cloud, and we have the probability of finding the electron at a given energy level. But that is the first result, or the first experiment. So let's do some examples using these equations, all right? And then we can talk about the quantum effect, the Heisenberg uncertainty principle, and other considerations. So what questions can you have in the final exam or in, well, yeah, in the final exam, right? So a question like this. So let's do this. You can be asked, find the wavelength of a given photon with a given amount of energy. So for example, find the wavelength of a 5.2 electron volts photon. All right, that can be a question. So remember that that's the energy of the photon, and we know that energy is h times frequency, or hc over lambda. So I make this equals to 5 electrons, but an electron volt you have to change this to joules, because H is 6.626 times 10 to the negative 34 joules second, and the speed of light you can use 3 times 10 to the 8 meters per second. So let's do that. So here you have 5 electron volts. To change electron volts to joules, you just multiply 5.2, sorry. 5.2 times 1.60 times 10 to the negative 19 Kelvin joules. That's equal to hc over lambda. All right. So 5.2 times 1.60 times 10 to the negative 19. H is 6.626. That's your H. And then we need the speed of light. And the wavelength. There you are. So wavelength equals to all that, 6.626 H C all divided by this. All right. So 19 plus 8 is 27, 10 to a negative 7. Right? 6.626 times 3 divided by 5.2 divided by 1.6, 2.4, or yeah, 2.4 times 10 to a negative 7 meters. Now, let's suppose that, let's suppose they don't give you the answer in meters. So we could change that to micrometers divided by 10 multiplied by 10, 0.24 micrometers, or divided by 100, multiplied by 100, 240 nanometers. Ultraviolet light. Yeah. Visible light goes from 400 to 700. So there you go. Any questions? I mean, it's just applying that equation. You just have to be careful with the units, that conversion here. Like that. All right. Oh, wait. Okay, let's use Vince's law. All right. I'm just gonna show you how to find the peak wavelength for the sun. All right. And let's use the accurate 5800 kelvins to show you how we find the peak wavelength and then also frequency for the sun. It's another type of question you can get. So find the peak wavelength for the sun, which has a of 5800 kelvins. Remember, guys, that's the surface temperature of the sun. The temperature of the core is about 10 million kelvins required to fuse hydrogen into helium. That is actually the temperature in the photosphere. That's the layer that you observe when you look at the sun. So to do this, we need to use this equation. Lambda times temperature at the peak is equal to 0.00290 meters Kelvin. All right. So the temperature is already in Kelvin, so I can directly find the lambda in meters. Lambda times 5800 in kelvins, sure, kelvins, 0.00290 meters. So clearly, kelvins become meters. So now we just divide 0.00290 divided by So I get lambda equals to 5 times 10 to a negative 7 meters. So if you multiply by 100 here, and divide by 100, you get, that's correct. Visible light, as you would expect. That's where you can see the sun. So you can see the peak radiation of the sun, this lambda peak, is in 500 nanometers. Normally, what we have discovered is that it's between orange and green. Peak. Yeah. Of course, that doesn't mean that all the radiation is coming from the peak. It's just the peak value. The energy is distributed across the whole spectrum. All right. You probably have heard that when there are solar mass ejections from the corona is the outer layer of the sun. If you ever see a solar eclipse with proper glasses, goggles, right? You can see part of the sun, that's the corona. Normally we photograph that part of the sun with gamma or even X-ray telescopes because the energy is huge at that point, right? So it can eject energy at those frequencies, all right? But the majority of the energy or the peak of the energy is given at that wavelength. All right. So there you are. That's Wien's law, Planck, the Planck constant. Let's see what else we have here. Okay, let's do a photoelectric effect. Photoelectric effect. It can be a question like giving a metal that is struck. So you have a sample here. You have a piece of metal and you have, now we can show you light like this, right? Dual. Photons with lambda 240 nanometers. They are going to strike that metal, and electrons are going to be ejected from this. So you have electrons or photoelectrons being ejected with a maximum energy of 2.58 electron volts. All right. They want you to calculate the work function of the metal. The work function of the metal. All right. So this one, you have to use the photoelectric effect equation. But again, you have to be careful with the units. All right. What are you being given? You're given the wavelength of the beam of light that is striking this metal. And it's ejecting these photoelectrons. Now, the photoelectrons energy is in electron volts. So I would suggest to find the energy incoming from light in electron volts. Why? Because at the end of the day, when we look at tables, or when we in photoelectric effect studies, we write down photoelectric or work energy functions, right? For metals in electron volts. That's the unit that we use for this type of experiments. So what you should do is find the energy of these photons. Remember, energy equals to K max plus W. So K max is already in electron volts. Let's find the energy in electron volts. Well, the energy is H frequency, but we're given the wavelength, so let's use Hc over lambda. Now, if I use this equation, this is your H, this is your speed of light, and the wavelength has to be in meters. Perfect. There you are. But that will give you energy in joules. 1 electron volt is equivalent to 1.60. So if I want to go from electron volts to joules, I multiply. If I want to go from joules to electron volts, I will divide by this. All right? So let's find E. In joules first. So 6.626 times 3 divided by 240. So 8.3 times 10 to the 10 to a negative 19 joules. Then divide and multiply. Yeah. So that's the energy in joules. Okay. Now I want to change this to electron volts using this. So the energy in electron volts is this guy divided by and that will give electron volts. That should be around 5, right? Yeah, 5.2. So 5.2 electron volts. There you are. So I found the energy of the incoming beam of light in electron volts. The maximum kinetic energy was, now I can find my work function. It's a simple subtraction. .62 electrons. There you are. There you are. So, 3 different applications for the concepts of quantum mechanics. We still use the Planck equation, so that's going to be for sure in the exam. And then Wien's law, how we find the peak wavelength. By the way, there, if you have this, you can find the peak frequency, right? I don't know exactly what equation. I have to double check the equation sheet, which one they give you. But if they were asking you for either of those, remember that if you have wavelengths, C equals to lambda f. So the frequency will be C over lambda. So that will be 0.6 times 10 to the 15. Multiply, divide. So around 6.0 times 10 to the 14 hertz. Right? You can just do it like that. That works. All right. All right. Now, in the next two slides, I'm just gonna show you a few questions that tomorrow we're gonna prove, or sort of prove, which is relativistic considerations for this. Because remember, photons are bundles of light, and light moves at the speed. Light, or a photon then, will move at the speed of light. So a photon is not a particle like the electron. A photon doesn't have mass. So we understand the idea of energy. How come a photon also has momentum? Well, you should remember that we found the momentum for an electromagnetic wave. The momentum for an electromagnetic wave is equal to the energy of the wave divided by the speed of light. Now, here is when we can get the de Broglie equation. The de Broglie equation comes from the idea of the momentum of a photon. Light is an electromagnetic wave. An electromagnetic wave has momentum. Then photons, even though they are just bundles of energy, will have momentum. So we know that relativistically, the energy, the total energy of a photon is equal to gamma, the mass, certain mass times this. That would be theoretically the energy. Now, what's this gamma? I want to show you this now because tomorrow you're going to see this a lot. Is the Lorentz factor. This nice factor here. Basically, the relativistic considerations of energy, right? You probably have heard that as the speed of an object approaches the speed of light, mass will approach infinity, basically energy. This comes from this. It's gamma times the mass. Think about it, right? If v approaches the speed of light, c squared over c squared is 1. 1 minus 1. 1 over 0. The limit is infinity. Right? Remember. This is a graph of 1 over x. When x approaches infinity, right? So that's what happens. The mass increases. So we can find technically the momentum of a photon, even though it has infinite mass, it's basically energy. We can use the equation that we proved before for the electromagnetic radiation. Energy over C equals to momentum. But now we know what energy is. Now we're talking about the photon. So what will be the momentum of a photon? Well, momentum is energy divided by c. And we're gonna prove the de Broglie equation. Energy of a photon is h frequency divided by c. But wait a second now. Frequency over c is h over lambda. So there you are. The momentum of a photon is equal to the Planck constant divided by the wavelength of the photon or the radiation. That's important. This equation is used a lot in the next experiment that proves that light behaves as a particle, which is the Compton effect or the Compton scattering. Because the Compton scattering is the next experiment that we have in quantum mechanics, in quantum physics, that show us that when radiation strikes electrons, they can interact like particles of masses m and m, m1 and m2. The experiment looks like this, and you probably have done this in physics 1 when you did the two-dimensional collisions. So let's show you this now. So this equation is on the slides, and I'm just going to erase that. Very important, by the way, the de Broglie equation using this de Broglie wavelength. Lambda equals to h over momentum. Now, you may say, but hey, wait a second, it's the same. Yeah, but the de Broglie equation is the wavelength for is the associated wavelength of matter. We're going to talk a little bit about this at the end. This is the associated wavelength. I'm sure many of you have talked about this in chemistry because we use this to show that any mass, or in this case, a stream of electrons, can behave as a wave at a given frequency or wavelength. And if that's the case, we can replicate certain experiments that we did in the past, like the Young double slit experiment, and observe the same pattern. And that's also in the slide, by the way. So let's show you the Compton scattering. And then we can go into that. Now, I want to be honest with you guys. The proof for the Compton scattering is very long. So I'm just going to show you the equation. And on top of that, we never really test Compton effect. But it's important that at least you know what this is about. All right? So at least let me show you what the Compton scattering is, how it looks like, and why it was the definite proof that photons behave like particles, or light behaves as a particle. Basically because of this. You have X-rays. So you need high energy photons. And you have an electron at rest. There. By the way, guys, if the electron is at rest, it doesn't mean that it doesn't have any energy. And we can prove using a special relativity that electrons at rest have an energy equals to mc squared. That's the energy mass of the electrons is squared. That's another difference from classical, right? So when the X-ray, we can ignore friction in quantum physics, in the interaction between photons and subatomic particles. So when they strike, when this collides with this, you will have that the X-ray will continue like this. This is some lambda, The wavelength will change to lambda prime because it's losing energy, but that energy is given to the electron, which is scattered. Aha. So we have an angle here, phi. What you're seeing there is what you saw in two-dimensional collisions, and you solve problems like this. If this is an elastic collision, and it is because we're talking about X-rays and subatomic particles, the electron, so there's no friction. So in elastic collisions, energy is conserved, and also linear momentum. So that's key, because the momentum of the X-ray here was lambda divided by, was h divided by lambda. The momentum here decreases because the wavelength increases. H divided by lambda prime. So lambdas change. Lambda prime minus lambda. Well, if you conserve momentum and energy, you obtain the following equation. The difference between the wavelength is equal to the Planck constant divided by the mass of the electron and the speed of light, 1 minus cosine of phi. That is the equation of, that's basically the quantum scattering equation. If you are interested, there is a, I want to see if I can show you guys the proof, or I can upload it as a part of the module. What makes this proof a bit difficult is, well, I mean, you have the energies here, right? Hc over lambda prime. But what about the energy of the electron? We're going to see that tomorrow, actually. But there is a relativistic energy for electrons that depends on the momentum. Let's see. Oh, yeah. It is. That's the energy of the electron after the scattering. It depends on momentum. The momentums are vectors. Momentum of the electron, momentum of the photon there, P final, P initial, so you can use vectors for the momentum conservation. And then you get a very long equation, but then terms will start to cancel. And you have this for momentums, and you end up with an equation like this. Okay? Of course, we have to remember that the energy before the collision is this and this. And after the collision is, well, hc over lambda prime, that. So, but it works out. It works out because this is here, square. So, and if you square this and you square this, it will cancel out. So I hope it works out. It's just very long. All right? Which is why we don't really test this. But what are the results of this? Well, that we can use classical concepts to prove the equation for quantum scattering, and that an X-ray loses energy and its momentum changes as it has a collision with a mass. An electron has mass. Look, when we talk about why we didn't talk about this before when we talk about electric fields, magnetic fields? Because we were using subatomic particles, electrons, protons. So you can accelerate masses and you can still use Newton's laws and Newtonian mechanics. Now you can't really use that because now you have photons. All right. Now, what this also shows you is that, well, an X-ray has momentum. That's the only way you can have this type of scattering. Furthermore, this is a Compton scattering. So the electron at rest gains energy thanks to the X-ray. And we have the inverse effect. And yes, this is known as the inverse Compton scattering. In the inverse Compton scattering, you have relativistic electrons, electrons moving at 30, 40, 50% the speed of light. And they can crash or collide or strike electromagnetic radiations in infrared or microwave, which have very small, which have smaller frequencies than X-rays or gamma rays. And what you see is that the electron will lose energy and the radiation will have a jump of energy in what we know as an inverse Compton scattering. All right, in that case, we have electrons colliding with electromagnetic radiation and electromagnetic radiation gaining energy. All right, so we see both. We actually see both. Where do we normally see the inverse Compton scattering? In accretion disks of black holes. Accretion disks of black holes are very turbulent regions where you have large amounts of magnetic fields and you have very fast relativistic electrons as they approach the event horizon, of course, right? All right, so now I can show you the slides, which summarizes everything we talked today. So that's your graph for the inverse Compton scattering. Here you have the equation. All right. So yeah, the wavelength of the outgoing photon is longer than the incoming because of the loss of energy. And then you have the de Broglie and the wave-particle duality, right? That a particle may exhibit a wave-like behavior. You may think that's just rearranging the equation for momentum, but not really, because that was a relationship that he found based on some experiments. The first experiment will be this one, the diffraction using X-ray radiation, right? You have incident and you have reflected beams. They are light, so the law of reflection will work. And you remember your d sine theta was the difference on path length. So he found that for crystal planes. And that will lead us to the diffraction of X-ray particles, right? What we see is that we can have patterns like we obtain when we have monochromatic light or coherent light. With coherent light or monochromatic light, that's what we had. But we know light are photons. These are photons as well, right? So these are high energy photons. These are low energy photons. And we have diffraction. So what de Broglie proposed with this and this is that you can replicate this by using electrons at a given wavelength. So we can see diffracting patterns with an stream of electrons. This is true even if the particle beam is weak enough. There you have it. So here you have an electron diffraction pattern. At the beginning, it looks like random electrons hitting the screen. As you keep going on the experiment, you start seeing bands being formed. 1, 2, 3, 4, 5, and then here, 1, 2, 3, 4, 5. So you can see this with an stream of electrons. There. Now, there is a problem with this one, right? So the de Broglie equation shows you that there is an associated wavelength for matter. Electrons, protons, they are all matter. So if you replicate the experiment of de Broglie, you may think that you are able to find the position of a fringe, and you can. But what about the speed, aka the momentum of those electrons? Well, let's take a look at the equation we have. Let's take a look at the equation we have. And let's see if you remember some of your chemistry. So in the diffraction experiment, we had that this was W. And I'm gonna use electrons now. Right? So you can have a screen here with some distance d. And on the first order, or at any order, sorry, you may have one of the fringe patterns in there. So that's your theta. Now, this is the vertical position of the electron. So you can say that the electron may be found there, but what are the chances that you know that? So we know that the equation for this is W sine theta equals to m lambda. What's lambda? Well, remember, lambda equals to h over p now. The associated wavelength, right? Because electrons have some velocity. Well, some momentum. All right? Okay. For the first order, we can say that W sine theta equals to lambda. And that happens to be the width of the maxima. Remember, at the center you have the maxima. So you want to find this width, use this equation. All right? So sine theta is equal to the wavelength of the electron divided by W. W is the width of the slit. Now, that wavelength depends on, like, now the wavelength is not just any wavelength that you can adjust. We're talking about electrons. So the wavelength is equal to h over delta p. Furthermore, delta y, that one, is d sine theta. Yeah, sine theta because it's a small angles, all right? So I can use that. Sine theta, delta y, which is the position of the electron, equals to d lambda over w. But lambda is this. So delta y, the position of the electron, is equal to d lambda h over delta p w, delta p of the electron. Oh, there you are. The delta y of the electron times delta momentum of the electron. So the momentum and the position are inversely proportional. Now, you can adjust these values to be less than or equal to h over 2 pi. So basically, the Heisenberg uncertainty principle, Heisenberg the equation is just that the position of the electron, and the momentum both cannot be known with the same degree of precision given this factor in between. So the more you know about the position, the less you know about the momentum, aka the speed of the electron. The more you know about the speed, the less you know about the position. That's the uncertainty principle of, that's the Heisenberg uncertainty principle. And that is one of the keys of modern. Oh, my bad. The limit. So that is one of the keys that lead us to modern quantum mechanics, because that's when we start talking about the probability of finding the electron at a given energy level, right? From there, we can have the whole idea of, and then from there, we move on into the Schrodinger equation, and that's when we start using calculus to solve to have different solutions for the Schrodinger equation, right? Basically, what we know in modern physics as particle in a box, and you get a wave equation in there. All right. So there you are. That's yeah, that's basically what I wanted to go over on quantum physics, guys. What I want to show you now very quickly is how we use the idea of photons in what you know from atomic physics, transitions, just very quickly, and then we finish with this class, and we finish with the class. All right. I don't know if you guys have any questions about this.
So, Professor, what will we do tomorrow? Will tomorrow just be a review day?
No, tomorrow I'm doing relativity.
Okay, got it.
Yeah.
Linear relative. These called linear.
Wednesday there is no class, remember. Oh yeah, by the way, I forgot to tell you how many of you are today. The final exam is on Thursday at 10 a.m. I don't know if you guys remember that. Okay, so I will publish the announcement after class, but the final exam is on Thursday at 10 a.m. except for the students who requested to take it before, with a valid request, of course. All right. All right. Let's see. So you maybe remember this from earlier in the semester when I talk about the electrons, the protons, and the models of the atom. All right. Remember that the electron was discovered in the 19th century, basically at the end of the 19th century. It was a negative charge. This actually shows why we thought current was due to positive charges. And what you're seeing there is a plumb padding model. So it was believed that the atom, yes, that the atom was basically a positive charge, and you have negative charges like stuck on the crust of the positive charge. Now, observations led us to understand that the electrons were not just static, but they were moving. That will be the Rutherford model, and later on the Rutherford Bohr model of the atom that led us to this model that many of you have seen in high school, right? So this model was widely accepted because it was known as the solar system model. Now, by then, we had already understood that planets move in elliptical orbits around the sun. There was no question about it. So it was very nice and elegant that in the study of quantum physics, in the study of subatomic particles, we had electrons also orbiting the nucleus of the atom. And as you can see, they were not really circular orbits. They were kind of elliptical. That's what we call it, orbits or orbitals. When you do the electronic consideration, you talk about the orbitals, right? 1s2, 2s2, 2p. So
what?
I was, yes? Oh. So that was okay. The problem was that this model was very good to explain the hydrogen atom. And I'm going to show you today, or a little bit, how we use the electrostatic force and the conservation of angular momentum to find the Bohr radius. Many of you have probably heard about that. The Bohr radius was the theoretical distance between the electron and the proton in the hydrogen atom. So, and from there you can have different results to study the hydrogen atom, which is a very simple atom because it has only one proton and one electron orbiting the nucleus. When you get to heavier elements, more complicated elements, that's when the solar system model doesn't really seem to work. All right. Now, this model has been kept because of simplicity. It's simple to explain to students in high school, especially, how electrons may orbit the nucleus and to show you energy levels, right? Many of you have seen the ground level, the first, the second. So you can still use this for that. However, it's important to show you guys at this level that we actually have electron cloud. And then electrons actually, as I just showed you, with the Heisenberg uncertainty principle, we may be able to find the probability of an electron to be at a given energy level. Okay? Now, so here is a problem with the picture I show you here. Orbiting electrons are accelerating. As you know, there is centripetal acceleration, so they should radiate. The frequency of this radiation emitted by a continuously radiating electron, right?
I can't.
Will have a continuous spectrum. So that is another problem, though, right? For example, let's take a look at this. Imagine you have a gas, nitrogen, helium, mercury. What we do in experiments is we can pass a very high potential difference, high voltage. Now, this gas will emit radiation. We can use a diffraction grating like I showed you last week. And we obtain what we know as the line spectrum. This is how we can relate sort of what we did today and what we did before. You know that radiation are due to photons. So these photons have a given wavelength. So this is what goes through the diffraction grating. What we observe are not really diffraction patterns anymore. We see spectral lines. Now, this is actually constrained in the visible side of the spectrum. Depending on the element, we call this the spectrum of hydrogen or helium or mercury, etc., etc. So you guys remember when we talk about the Doppler effect? When we talk about the Doppler effect for electromagnetic waves, I show you that you can have the source moving towards the observer or away from the observer. For example, in the universe, we have nebulas. For example, when you see there is an emission nebula, we know it's an emission nebula because of the reddish pink color, because of the stars that you see are embedded. If we take this picture in infrared, you will see a lot of more stars that are hidden due to the gas and dust of this nebula. So this is due to hydrogen emission. Now, nebulas like this may be due to the expansion of the universe, they may be moving or receding away from us. Now, because the universe is expanding very rapidly, they will be receding at relativistic velocities. So the Doppler effect shows you, and I'm going to show you that tomorrow actually, even though I'm not going to test you on that, but at least so you guys learn. So the Doppler effect can show you the redshift of galaxies or the redshift of objects receding from us. Basically, this spectrum of lines will be shifted towards the right, because the wavelength increases. If the wavelength increases, the frequency decreases. So it's always shifted towards the right. So that's very important for the study of atomic physics, because we have that each atom of each element has its own particular emission lines. All right, guys. So you guys should know this, even though, again, it's not really going to test you on this. But if you take a class on astronomy, for example, one of the things I go over is this: emission lines, absorption lines. What's the difference? These are the lines that you get from this gas. Now, let's suppose that you have a star here. This gas may be the atmosphere, or maybe a cloud, like this, in between the star and us here on Earth. Normally, a star, as I talk about today, is a perfect black body radiator. So a black body radiator will emit light continuously. So continuously means the rainbow spectrum, from red to blue, and purple, without any lines. However, realistically, when we observe any star in the universe, like the sun, for example, we see a lot of gaps. Why? Because of the emission of particular atoms that may be, and as you should expect, most of those are due to hydrogen and helium. Let me just show you that. So the spectrum, let's see if I can see. Oh, there it is. So this is the sun spectrum that we obtain with observations at different wavelengths, right? So you can see the continuous spectrum of the sun, right? From red to blue. And you see a lot of gaps in there. Those gaps are due to the elements that are in the sun's atmosphere that go through before they reach the Earth. And all of that is explained by excitation of atoms. And what's an excitation of atoms? Is electron transitions. And how do we quantify electron transitions? By this. And I hope many of you have seen this equation before, right? For the hydrogen atom, that's how we obtain the wavelength of a transition. The inverse of the wavelength is equal to the Rydberg constant, 1 over, well, we use 2 squared because we use the Balmer series. There are different series. There's the bracket, the Parshian, the Lyman, right? That tells you the final energy level. So 1 over 2 squared minus 1 over the initial energy level square. It can be 3, 4, 5. So the electronic transition that you guys studied before is due to the emission or absorption of photons by the electron. Now you know that because we have talked about that today. But these electronic transitions emit radiation, as you would expect. And that's the wavelength of the transition. So we have this, and then we also have the Bohr model of the atom. All right. So the Bohr model of the atom, and we are gonna almost finish with this, allows you to find the distance between the electron and the proton. And by the way, it also explains why the electron doesn't fall towards the proton, right? We know that there are 4 fundamental forces in nature. And the nuclear strong force is the one that acts on top of the electromagnetic force. All right? So you remember this. So the electron is, even though it might be going at constant speed, which is already a, well, actually, it might be correct. It's not really going in a circular orbit, but if you approximate this to a circular orbit, it has some radius r. Now, that's the distance between the electron and the proton. Now, you know already that there is a force in between, electric force. But if it's in circular motion, the electric force equals to the centripetal force. So the first equation will be Coulomb's law divided by, okay, and let's say here Q is the charge of both electron and proton, right? All right. I showed, well, it was on the slides in the chapter 15. What's the other thing that we have now to take into consideration? Well, this. We know that, and there are 2 ways to do this, by the way, but this actually shows you what we know as the angular momentum of the electron. Because any object that is going in circular motion has an angular momentum. The way you can prove it is by remembering that there is an associated wavelength for the electron. So that's actually the picture that we should think about. So the circumference equals to a number, integer number of wavelengths. But wait a second. The electron has an associated wavelength, which is equal to, and what's momentum? There. So 2 pi m e v r equals to n h. And on the slide, they tell you that this is the angular momentum of the electron, capital L of the electron equal to nh over 2 pi. So that's our first result. If you didn't know, well, there you are. So the angular momentum depends on the first quantum number, h over 2 pi, which at the end, in some textbooks, they call h bar equals to h over 2 pi. Now, how do I find the radius? Well, from this and this, I can find the Bohr radius. And the Bohr radius was a very important result at the end of the 1920s. Because it basically shows you that that's where you will find the electron. So if I cancel that, I get the kq squared divided by mv squared equals to r. But I also have this. 2 pi mass of the electron Vr equals to nh. So I want r. So V, I don't need velocity, nh over 2 pi mr. That I put in there, and we have kq squared over m. V squared is all this square, n squared, h squared, 4 pi squared, m of electron squared, radius squared, all equals to radius. So what you will have is, you will go at the top, this will go over there, and you will have r equals to n squared, h squared, m, n squared, h squared over 4 pi squared, k q squared. A lot of those are constants. K is a constant, 4 pi, h, the charge of the electron, so, and the mass of the electron. Yeah, there's the mass of the electron. All of these are constants, right? So we can find the Bohr radius as a function of a constant, and let me show you what that constant is. There. That's the constant. 5.29 times 10 to the negative 11 for n equals to 1, of course. That's the Bohr radius. All right. And then as a function of n is what I just showed you on the board there. And then you can find the energy of the energy level. In electron volts is negative 13.6 electron volts. For the hydrogen atom will be just negative 13.6 electron volts divided by n squared. That's the lowest energy, called the ground state. All right. And that's what you have. You can have different series doing different transitions, right? Electron jumps in the first excited state, or in the partial series, the electron jumps in the second excited state, right? Here and here. This is what I show you on the board. This is what I just show you as well. And to finish, just to introduce you guys the 4 quantum numbers that were described and we obtained from the study of the hydrogen atom. The n number that we've been talking today is related to the energy of the electron. That will be the principal quantum number. The angular momentum, it's there, is your L, right? That goes from 0, 1 to n minus 1, so that's the limit. The magnetic quantum number from negative L to L, and that's the equation there. And then the spin, negative 1/2 and 1/2. All right. That's why we did all these studies of quantum physics, guys, because from there we can use it to investigate the hydrogen atom, and specifically the Bohr model for the hydrogen atom. So that's the only thing I want you guys. This section is not going to be in the exam. The only thing that you need to review that is going to be in the exam is up until photoelectric de Broglie, until de Broglie. All right. So I will say, let me show you actually. I will focus on Wien's law, the Planck equation, the photoelectric effect, and the de Broglie or the momentum of the photon. Don't worry about quantum scattering. All right. That's the Broglie there. Other than that, that's the only thing. If you want to practice problems again, guys, you can go into modules. Chapter 26 has 2. This one will have relativity. So for relativity, I will go over that tomorrow. That's it, guys. Almost the end of the course. So any questions? Okay, so the final exam is already been done. Look, guys, there is a question on relativity, just one. So, I mean, it's probably not going to be a big deal, but at least if you are interested on that, I will say come tomorrow, all right? If you want to start studying or you want to catch up with assignments, I understand, but there's only one question of what we're doing tomorrow. And as I said, just 2 questions maybe on what we did today. Most of the exam is up until what we did last week. So basically until exam 3, adding diffraction and interference. Wednesday, there is no class, but I will be in the building if you have questions, all right? And then the final exam is on Thursday at 10 a.m. Now, any questions regarding that? All right, so the lecture has been recorded. I hope that you guys learn. That's the main thing, guys. On these topics is more about learning.